Okay, so let me start by sharing your screen. Uh, are you able to see my screen?
Yes.
Yes, sir.
What are you able to see now?
MTech thesis supervisor slide.
Good. So you can see that problem, right? Good.
Yes, sir.
So this, yeah. So this was the problem that was already discussed in the class, right? But just let's start from here. So in the last class, we were looking at this problem, and we converted it to a flow problem in which we kind of assume that this for each faculty, right? They only give us only one. They can take only one student, right? And we kind of wrote an LP for that also. Everybody fine with this? Everybody managed to go over this, whatever
Yes,
was
sir.
done in this class? Okay. So let me start with then on a slightly more general thing. I mean, again, this I think the MTech CS students must have seen it in the discrete math course, and MTech CS students have not seen it. So basically, it is what is called flows, network flow. So what is the network flow? So basically, it is a graph G that is a set of vertices and the edges. And now this is a directed graph, okay? And you have the set of weights which are from the edges to real numbers, okay? And in fact, it is usually positive. And you have two particulars, and the G is directed. And you have two special numbers, S and T, in the vertex set field. So for example, I can have a graph like this. Let me just back. That's fine. And you have some weights assigned. So I can define this EHS as the S, this is T, and this is the where U1, U2, U3, U4, U5, U6, and U7. And we have the edges, say, something like that. Okay. Now, so you should always think of the vertices as some kind of a, so it's, think of this one as a kind of a network in which you have a start state, you have a terminal state, and you have some nodes. These are the kind of some stations in the middle, and in each of the edges, it's kind of a capacity that is there. So sometimes it's weights are considered called capacities of the edge. So idea is that you cannot send more than 2 units of something on this way, or you cannot send more than 1 unit of something on this way. And your job is basically, you can think of this 2 to be equal to the so this weights to be equal to so say there, so all these things are kind of a pipeline. They're like they are one-way pipeline kind of stuff. Okay, and you have one-way pipeline, and you want to say put in water from this side, and you have to take out water from here, or put in oil from here and take out oil from here, right? And question is that how much amount of oil can you pass from here to here? If I push in oil from S, how much amount of oil can go from S to T? Right? And this basically, what does it mean? Is that we want to come up with a flow. So what is a flow? So a flow is nothing but, so flow say F is also nothing but a set of, is a assignment of amount of element flowing on each edge. Okay, so we have this capacity or the weights. Maybe I can call this one as capacity. That would be easier for me to write. So let's just call this C. Okay, so all the blue colored here are the capacities. Okay. And what we want is a flow with a set of the edges, and it has to have it has to have 2 properties. Number one, so if in a particular edge, right, if the maximum amount of capacity is C of E, that means this is the amount of things that you can pass through that edge, then you should flow less than or equal to that amount through that edge. Okay, so in fact, this is positive, so it's also has to be always get 0. So you cannot make more flow through an edge more than the capacity. And the another thing is that in each of these nodes, right, you have some amount of stuff coming in. Say, for example, if I push in 2 amount from here, so I push in 2 from here. After I push in 2, I can of course send half from here and 1 from here. Can I do that? Of course I can, but then that would cause an accumulation of, I have 2 amount of things coming in and only half and 1 is going out. So I will have an accumulation of 0.5 units here. These are not allowed. So these are not nodes as kind of storage places. So these are the things that you want to flush out. It cannot store. Okay. So this is not allowed. Okay. So what you can do is that you can say, okay, I will send 0.5 from here and 1.5 from here. And that is fine. Okay. Yeah. So, so what does it mean? That for all vertex, okay, consider the sum of the amount coming in. So UV, but U is all the possible vertices. So look at all the flows coming into a vertex from various places. This should be equal to the amount of flow going out from that vertex to all the places, right? So neither can I store things over here, nor can I produce extra thing from here. Okay, and this is a flow. And what is one thing is that what is the weight of the flow or the value of the flow? Value of the flow F. So this is the amount of the quantity of stuff that is one can push from the source to terminal. So how can that you, what is that? It is of course the amount of stuff that are going out of S, right? This is also the amount of stuff that is coming into S, T. Oh, so sorry, I made a big mistake over here. So when I was telling phi for all phi not equal to S and T, S and T are the only two places where I am not allowed to, I mean, I am not forced to ensure that what is coming in is same as going out. Because you can think of it here that there is a massive tap over here. You can keep on pushing from here. And from here, there is a big drainage that goes out. Right. So except for these two vertices, every other vertices, they maintain the this property that whatever comes out, exactly same amount goes out. And for the S and T, that is not the case. So you can say that this is equals to summation of flow from S to U for all the U. And this is actually, you can prove it, that this is exactly equals to the amount of flow going into T sum over all the. Is this clear? Is this fine? Any questions about this concept of flows? Hello?
Yes,
It's
sir.
clear, it's
Okay.
clear, sir.
It's clear. Okay, good. Now, okay, so what is the goal? So most of the time, the goal is okay to find a maximum flow. Now, see, why I saying A, because there might be more than one flow that achieves the same value. Okay, I can pass a maybe I can pass a particular thing from here along this route. I can also pass the same amount from this route. Okay, so there might be multiple flows, multiple flows that give the same value. Now, okay, so now can you guys? So let me give you this one. Okay, use LP to find the maximum flow, a maximum. In a net. I will give you a couple of minutes. Why don't you guys try to write down the LP for this? Let me see. Can you maximize this?
It's already there in the picture, right? In the definition of flow. Hello.
Yeah, I mean, you have to kind of maximize something and you have to put some constant, right? I'm not.
So maximizing will be just one of the equalities in the value of flow.
Maximizing will be one of the inequalities.
I mean, maybe like let's maximize u belong to v f of s comma u.
U belong to V, f of s comma u. Just some particular thing or summation of that.
Yeah.
Okay. Yeah, I'm not saying that it is hard. Okay.
And rest of the equations are already there.
Right.
Recording in progress.
Hello. Hello, can you hear me?
Yes, sir.
Yes, sir, we can hear you. Yeah. Yeah, I'm sorry, I just changed. Use this one because I couldn't see the audiences were there. Okay. So, yeah, so you're right actually that the LP that is there is pretty simple. Okay, it is actually right, completely right. What do? You maximize. Of course, you want to maximize this. Once you maximize this, right? So maximize summation of S of SU over all the U. So this is the maximize the flow such that what are the other properties are there? Of course, I have to satisfy both this law, okay? Such that number one, f of E is less than or equal to C of E for all E. So these are m number of inequalities. And the other one is that for all vertex, S f of UV is actually equal to f of VU for all the vertices. So these have n vertices. So these are like m of them, and these are n of them. And of course, I have this A is bigger than or equal to 0 for all. Fine. Good. Yeah. Hello. Yeah. So this is a. So are all of you convinced about this one?
Yes, sir.
Oh, excellent. So what does this mean? That if I give you a flow, okay, so if I give you a graph, so given a network flow instance, meaning this is a graph, okay, you can find a maximum flow in polytime. Okay, why is it polytime? Because I had told you that this is a LP. This is not an ILP. You note that this is actually an LP. And so this LP, of course, can be solved in polytime. This is something that I had told you. I promised you in previous class, right? That you can. So you are using the fact that LP can be done in polytime. Okay, good. So now, why are the flows interesting or important? Now, in the last class, we were asking questions like, okay, we were looking at matchings. So what are matchings? So of course, if we think of them as a bipartite graph, so G is a bipartite graph, the A, comma B, comma edges. Okay, and I want to, so and M, which is a subset of the edge set, is a matching if for all A in A there exists, just one second. There are at most one vertex in B such that one vertex B in B such that AB is in M. And similarly the other ways, right? So for all B in B, there exists at most one vertex A in A such that A comma B is in E. So this is the definition of a matching. Okay. Now, if both of them are, instead of at most, if I make them, so if I make this one into exactly, there exists exactly one vertex, then this is a perfect matching with respect to A. In other words, every element of A has a corresponding matched vertex. And similarly, if in this case, if I replace this at most with exactly, then I get a matched vertex in, then I get a perfect matching for B. And if both of them are exact, that means every vertex in A is matched to a particular vertex in B, and every vertex in B is matched to a particular vertex in A. Then this is a perfect match. It's called a perfect. So I can have perfect matching with respect to A. I can have perfect matching with respect to B, and I have general perfect matching. A general perfect matching is basically a perfect matching that is perfect with both A and B, right? And there might be times when there are no perfect matching, neither with respect to A nor with respect to B. Okay, and in that time, what one might want to do is that find the maximum matching. What does maximum matching meaning? Means find the number of edges in the matching. So the maximum number of edges are vertices in A and B that are mapped. Okay. So in the last class, we saw that a matching can also be written as a linear program. Okay, rather than an integer program, right? So a matching, okay, a matching can be written as an ILP. Now, what it means is, of course, you can use ILPs to solve the matching, ILP solvers. But ILP is not polynomial time, right? Fine. So, okay. So that's a problem. But okay, so in this class, let me look at how we can solve this matching and also the what is called an integer flow kind of stuff in polynomial time. Okay. So this is so you're fine with till now. So we have this matching, which is basically so if I convert this matching into an LP, not an LP, into a network flow. So this is what we can do, right? I have this matching. Okay. say I have this matching, this is the A side, this is the B side, right? And I want to find the maximum matching. So what I can do is that I can say that, okay, fine, if I have a maximum matching, why don't I put in I start vertex S, I add a sync vertex T, I put edge weights 1 for each of them, and I put all these edges, I can say put infinity, or I can put say, okay, I can put 1. Yeah. So all of them. So if I solve this problem, if I solve the flow for this problem, what will I get?
Matching.
We'll get matching.
Yeah.
Why? Can you tell me why?
I mean, not necessarily matching, but maximal matching will get.
Why? How?
Sorry.
Why will I get maximum matching?
So here, okay, any okay, water out of S has to pass through wet cell from here, right?
Sorry?
Water out of what? From the source.
Yeah, from source.
It has to pass through both widths of A and both widths of B. It can't.
Yes, that is true.
Now, if at all the maximum flow is possible, then it has to go through maximum number of what vectors in here set here, right? Because each
So
of them
what
has-
happens if I just send, say, if I send 0.5, so maybe I use different weight cost here. Okay, so I say send 0.5 from here, there also 0.5. Okay, here I send 1, 0.5 goes here, 0.5 goes here. So this is 0.5, I get 1 over here, and so on and so forth, right? So it is possible that I might not be exhausting all of them. I might not be sending one flow in each of the edges.
No, but there might be another flow which is equivalent to that value, right? Which uses the
Yes.
exact capacity.
Yeah, but you're right. You're completely right. But can you see and prove how it is?
No.
Okay. So this is a theorem that was done in your in the MTech CS discrete math course. Okay, and this is a very important theorem that was done. Okay, and the theorem is that if a graph or a flow or network has integer capacity, then there exists a max flow with integer flows. Okay. Then there exists a max flow with integer flows. Now, this is not an easy theorem to prove. Okay, I will prove it. Okay, and in fact, it's a very algorithmic theorem, and that's why I'm doing it in this course. Okay, and this is also kind of give you a different thing. So, okay, so if this is indeed the case, okay, so this is a theorem. So if this is indeed the case, then what happens? Then in this flow that we have drawn, whatever 0.5 and all those things cannot happen, right? I mean, it can happen, of course, but if there is a max flow, then that max flow can also be attained by a flow where you use only integer weights. Integer weights means 0 and 1, right? So basically, it will always be like, okay, I'll pass 1 from here to here, 1 from here to here, and 1 from here to here. Very good. Because this capacity of this one is 1, so and the capacity of this one is 1. Okay, so there will be only one amount of unit that can go from here to here. Right? And therefore, what you will have is nothing but, if this flow, so if this graph has a flow of size t, then you can find a matching of size t. Okay, I'm not giving you the full proof of it or formal proof of it. You think about it. If you're not convinced, let me know. On the other hand, if there exists a matching of size t, so say this is a matching, say, in that case, I can always send S to all of those vertices that have matched in A, and a edge that will go and an edge from those vertices that are matched in B, and use the matching edges to pass T amount of edges to from S to T, T amount of flow from S to T. So for assuming this theorem, this flow problem actually solves the maximum matching problem. Okay, so what do we see? So where are we? Okay, I have not yet proved the theorem, and this is something that I will prove it to you soon. But what we were was that we can see that the flow can be solved, max flow can be solved in LP in polynomial time. A matching can be written in ILP. Okay, or a matching can also be written as a integer flow problem. So matching can be written as an ILP, doesn't guarantee that it can be solved in polynomial time. But when I write the matching as a flow problem, then what I observe is that all the edge weights can be made integer. Again, if I use just simple max flow algorithm, then I might not get a matching, but at least the max flow, if the max flow of this matching is T, then I know that there exists a matching of size T. Okay, and this is something that one can, I mean, that's so this kind of shows that how a matching can be made into a polynomial time algorithm. So this is a very important thing in which you see that just because some problem can be written as an ILP doesn't mean that it cannot be done in polynomial time. Okay? It might be that this can be done because it's a special structure that comes in. A flow is a special kind of LP. And that what it helps is that any flow in which the values are capacities are integer, you can actually, the max flow is same as the max flow for integer value flow. And this is something very crucial. Okay, but this also doesn't tell you how you can use max flow to come up with a matching. You can say that, okay, I can use max flow on this problem. If the max flow value is T, then I know there is a matching of size T. But that is not necessarily going to give you a flow of integer weights. Okay, so okay, I have not, of course, described to you the LP solution, how to come up with a design and algorithm for solving LPs in general. But now I'm going to tell you an algorithm for solving how to solve the this problem, this integer flow problem, at to some level at least. Okay, so this is something that we have done in our discrete math course, and maybe I can ask someone who was there in this one. Do anybody remember what
Yeah.
theorem I'm kind of talking about?
Max flow min cut will solve this because I have a minimum number of cards that will have integer capacities. So if I take them, they will make the perfect matching.
Yeah, I mean, so that will make the perfect matching. That is one thing. Okay, but yeah, so you are kind of solving it using the mean cut theorem, right? But I am saying that, okay, so you are right. So in the discrete math course, we had looked at this something called the max flow mean cut theorem. Mean cut theorem. I am not going to prove this theorem in this course. Okay, I am not going to prove this theorem. Okay, so it's, and this is something that if you guys want, you can please go back and try to look it up. What is it saying? What is the cut? What is the mean cut, and so on. But instead, I will prove how to. So I will instead give you an algorithm how to solve an integer flow problem. Okay, and this flow problem, the algorithm is something that is same as the max flow mean cut theorem that was done. Okay, so the thing that is told is what is called as the Ford-Fulkerson theorem. So it is almost a greedy theorem. Okay, so let me. I had this picture that was drawn earlier, right? I need to copy it. Maybe that will be help my life. Okay. Okay. Okay, so say I have this. You can all of you can see my see this picture.
Yes, sir.
Yeah. So I want to find the maximum flow from S to T. So what do I do? The first thing is that you greedily find a path from S to T and push as much flow as you can through that path. Okay. Say, for example, let me see. Can I have to think about some idea? Yeah. Say I first path that I find, maybe I'll is go from here to here, then here to here, then here to here, then here to here, and then here. Okay, so this is a directed path. Okay, so I mean by here I meant that find a directed path. Okay, from S to T. And from this path, how much amount that can be sent? Okay, since the minimum capacity on this path is 1, okay, I say that okay, so let's start with pushing. So I can send 1 unit on each of these waves. Okay, so it's basically says that okay, I have managed to find a path from S to T and have sent 1 unit of flow from each of this path. Right. Now, okay, so now what do I do next? So once again, let me think a bit. Yeah. So now I can come up with another path, right? So the next thing is that I can come up with another path, but think of it this way, okay? See, there is a from this path, 1 unit of flow is coming, right? So what it means is that so at this point there is a 1 unit coming from here to here. Okay. Okay. So sorry, I've overshoot myself. So because of this 1 unit coming, let me write down what happens here. So the capacity now here has gone down from 3 to 2, right? Capacity here has gone down from 4 to 3. Capacity here has gone down from 1 to 0, right? Now I cannot pass any flow from here. Capacity here has gone down from 1 to 0. Capacity here has gone down from 1 to 1. Okay. Now I can come up with another path. Okay. The second step that I can think of is that I can come up with okay, find another path. From S to T. What do I mean by find another path? So maybe I can find another path and okay, if I again go from here to here with 1 unit, and we can see this one from here to here with 1 unit, from here to here with 1 unit. Now, after coming here, I don't know where to go. I cannot, but I can go from here to here with 1 unit, and I can go from here to here also with 1 unit. Right? So I can come up with this path. So maybe I should draw this path that is there. Okay. So maybe this initial path that was there was S, U4, U3, U6, U5, and T. Okay. Now at this time, I have find a path through the edges which have positive capacity. And here I can send the next one that I can come up with that is U4, U3, okay, then again U5, and then T. And I can again see that here on this path, then there is this one that has positive weight 1, and that is the maximum. This is the one. So I can only push 1 unit from here. So in other words, what I will do, I will say that okay, instead of 1, I am pushing 1 more unit over here. I'm pushing 1 more unit here. I'm pushing 1 unit through here, and I'm pushing 1 more unit here. And I update the set of edges capacities 2 to 1, 3 to 2, 3 to 2, and 1 to 0. Now at this point, let's think about it. you can send from S, there's a 1 unit here that I can send. I can send 2 unit here. From here, I can of course go back to S, but that's completely useless because I'm going in circles. I can come to here because I still have 2 units over here left. But after I come here, I don't have anywhere to go. So does it mean that I cannot push any amount extra from S to T through this path? Right? It is exactly like that. Okay, I will use a different color. Let me use a different color. What happens if I use this one? Okay, I'll go from S to T. I go from here to here. There's still 1 unit left, right? I'm all of these are fine. I come up to U5. At that U5, I see that there is no non-zero capacity weights going out of U5. But at the same time, I can see that there is 1 unit coming from U6 to U5. So what can I do? It's like U6 is giving 1 unit to U5. Right? So what U5 can say is that, okay, see, why don't you do one thing? U6, you keep your this thing that is coming from your side, why don't you keep it to yourself? Or direct it through some other route. Okay. In other words, you can say that, okay, I will push 1 unit back. It's like 1 unit is flowing from U6 to U5, 1 unit is flowing from U5 to U6. So U5 and U6 have kind of cancelled out each other. But after coming here, I can then pass 1 unit from here and 1 unit from here. Now, what happens effectively if I can do that? Let's see. I can say that in this first one, S2, so the path that I have got is what? S to U4, U4 to U3, U3 to U5. Now, this is the most weird part. U5 to U6, then U5 to U7, and then to T. So what is basically effectively happening? I am sending 1 unit from S to U4. Fine, extra. I am sending 1 unit from here to here. That's also fine. Here also I'm sending 1 unit extra. But after coming here, I'm saying that, okay, you take back your unit. So I'm pushing minus 1 unit over here. Okay, I'm going opposite to the flow. And then I'm pushing 1 unit from here and 1 unit from here. And amazingly, see that this rule, this Kirchhoff's rule, which is basically no stagnation is allowed at any node, is satisfied. Okay. See, this is something that, by the way, we play a lot, many times, right? Say there are 3 friends, right? So there's you, there's you, your friend 1, and your friend 2. Sorry. Hello. Yeah, your friend 3, right? Your friend 1 has to give you 5 rupees. Or maybe nowadays nobody talks about 5 rupees, say 500 rupees. Okay. And you have to give and you have to give your friend, right? Say 200 rupees. And F1 has to give F3 100 rupees. Right? Forget this. So one way of doing it is that you can tell your friend, that, see, good. So you give me 500 rupees. Fine. So to start with, you give me, come up with a different set of colors. You give me 500 rupees. Good. This is what I've got. Now you can say that now I can give the friend 200 rupees. That is fine. And you can give this friend 100 rupees. This is one way of going about it. Another way of going about it is that you can say that, okay, but since you have given 500 rupees and you have to give F3 anyway 100 rupees, why don't I return back 200 rupees to you? And you instead pass on 100 plus 200 rupees to your friend. Okay, a bit more complicated. But what happens as a result is that this whole two things together basically becomes what? He is just giving you 300 rupees. So this is exactly what is happening here also. Because our amount of unit is passing from U6 to U5, it's like it is pushed back and it's negated. And the issue is that I cannot pass, can I send more amount? Can I send even more amount? No, because if I send back even more amount from here, if I send more than 1 unit back, then I am going to send minus some unit to the flow. I'm not allowed to send minus some unit in the flow, right? And if your friend is giving me 500 rupees, I can only return that 500 rupees to your friend, not anything more than that, right? So in other words, what is important here is that you don't necessarily find a path, okay? What you find is something different. You find, I can erase this part here. It's all about finding a so so after you have done with the first step, say, then the next step would be, okay, make an augmented graph. What does augmented graph mean? Augmented graph meaning the capacity of every edge becomes the original capacity of every edge minus the flow that you are sending through that. Okay. And so this is, okay. And another thing is that the capacity of every UV is how much? Capacity of every UV is the actual capacity of the edge UV plus the amount of flow that is happening on the other side. Okay, flow that is going from V to U. So from V, so from U to V, there was some capacity that was there, right? So there are 5 capacity here, but now there is a lot of flow coming in through this part, right? There is the 6 flow is coming from this side. What it means is that I can not only push back this 5 amount, I can also push 5 units here. I can not only push 5 units from here, I can also push back 6 units from here. So you update the capacity of everything as like this. Okay, in fact, I mean, this should be the, yeah. And this is what you consider an augmented path. And once you have done this augmented graph, and then you can find a path from S to T in the augmented graph and push maximum amount possible. Through that path. Okay, and update. And you keep on repeating these two things. So you find a path from S to T, push as much flow that you can send. That causes a kind of a augmented graph. Okay. You look at the augmented graph and again find that path from S to T, push as much thing that you can send from there. And again, you can push that much flow and you keep on doing it. Okay, you keep on doing it. Now, is it clear? Hello? Is this algorithm clear?
The augmented part is not clear.
Augmented part is not clear.
No.
I mean, did you understand that why, how did I push this amount here back? Did you follow that?
Like, even though the direction of the edges
Yes.
reverse, like you're reversing it and pushing it, right?
Yes. Okay. I mean, okay, good. Let me just repeat again. Okay. Maybe this will help you a little bit here. Okay. So, okay. There's S and T. Okay. And there's two vertices, U and V. So I start with finding a path from S to T. Right? At that time, how much amount of flow am I sending from S to T? I'm sending 1 unit from this S to U. I'm sending 1 unit from S to U to V, and I'm sending 1 unit from V to T. Right? At that time, how does my graph look like? Let's say, okay. So if I draw this graph once again, okay, there's ST. There is a flow that goes like this, right? There's a flow of unit 1. And then there are two paths here, S to V and this one. Correct. Okay. So these things have been taken care of. So the capacity, I don't have any more thing that I can send off from S to T using non-zero capacity. But what do you think is the total flow of this graph originally?
1, right?
1? Think of it. What is the total maximum flow of this graph? 2. It's 2 because you can send from here to here 1 unit and here to here 1. Right?
Yes, yes.
But I have already, by some chance, I picked up this vertex, this path, and I pushed in 1 unit. But now, just think of them as kind of a canceling kind of stuff. Okay. So what happens if I say that, okay, fine, now I am going to what happened? So I push 1 unit from here to here. Okay. Now here I can push 1 unit from here to here, and I can push 1 unit from here to here. I know that. But how do I transport 1 unit from here to here? At this time, this person U, so this vertex U is giving V 1 unit of flow, right? So think of it as water, okay? So 1 unit of water is flowing down from U to V. What happens if I push 1 unit back and try to push it through? What happens? Shiva Kumar?
Yes, yes, yes. So like,
Huh?
then we can have a path from S to V, V to U.
No, forget that. If somebody gives you 1 unit and you give back 1 unit, what happens?
0 Raman.
0 unit, right? Very good. So, but it is almost same as saying that, okay, you send me 1 unit, I send you 1 unit, right? And if I push that, then after doing so, I am going to send 1 unit from here. From here, U to V is 1 unit and V to U is 1 unit. So total amount of mass coming from U to V has kind of cancelled each other, right? 1 minus 1 is 0. And I push this unit 1 here. So I somehow, this is 0. So what happens is I am therefore going to send 1 unit from here at the flow, 1 unit on here. That is what effectively comes in. But I can think of it as I send 1 unit like this and another unit like this. And these 2 units cancel each other.
And
Sorry?
this is clear. What about the formulation of the capacities, new capacities?
Yes, what is the formulation of the capacities, right?
Yeah.
So if I have a capacity, so how much, so here, right? Initially I had a capacity, so look at this one, right? Initially I had some capacity, okay? So initial capacity I have a C of UV.
Hmm.
So maybe let's look at this one. C of VU. What was the C of VU? C of U was something, right? This is the amount of element that I'm allowed to push from V to U.
Hmm.
Okay. Fine. So maybe there was a path. Let me maybe draw this one. Maybe there is another edge from here, which is at unit 2. Doesn't matter whether that path exists or not. You don't need that. Actually, maybe just to for your okay. Let's assume a simple thing that will help. Let's assume that if the capacity of UV is bigger than 0, then capacity of VU is 0. Okay, to start with, meaning if you are flowing from U to V, then you don't flow back from V to U. Okay, let's leave with this. Okay. So in that case, what happens? So if I have a capacity from U to V, this gets updated by, you have this capacity of U to V minus the flow that goes from U to V. Okay, so this is if the capacity of UV was bigger than 0, right? And if capacity of VU was 0, then I have to update it because I am going to find out edges through that capacity, right? It's like, yeah,
Capacity of UV only, right?
it would be not the capacity of UV, it will be the flow of UV. See, and if so then capacity of UV is not equal to capacity of VU, right?
Mhm.
It's a directed graph.
Yes.
So how can capacity be same for both sides?
It won't be, but like,
So, but I have to
we are
update.
not
right?
sure, right, how the capacity function is defined. It can be same as well.
Can be same, but let's assume that this is the case. Okay,
Okay.
let's start with this because I mean this is not something that you need it. Okay,
Hmm.
but this will make your life simpler. You'll have able to understand it better. Okay. So
Okay.
capacity of uv equals to 0. There is no h from going from v to u. Okay, to start with, there is no h from v to u. Okay? So if there is no h from going from v to u, there but this capacity of u, but if from u to v some unit is coming, then I should be able to push that unit back. So this should be equals to uv. So u to v. So right now, for example, here there is no path from v to u. There's no h from v to u. Nothing like that. But since one unit is coming from u to v, I can therefore push back one unit back, right? So the capacity now gets produced. It's an artificial capacity that's come up. Just because you are giving me one unit, I can push one unit back to you. So that means in that case, the capacity of VU therefore becomes the amount of flow that is coming from U to V.
Yes, sir.
Okay, and that's the augmenting graph.
Yeah, that's fine.
Okay, is it fine?
Fine, sir, fine.
Okay,
So in the augmented graph, you have to draw the
you have to
VU.
draw a new edge
Yeah,
that is not there on the original graph.
yeah. So augmented graph will become a multi-edge graph.
It can become a multi-edge thing or something like that.
Okay.
Is it clear this algorithm, what the algorithm is doing?
Yes, sir. So in the like
Yeah.
after finding the next augmented path, so again
Yeah.
we'll search for the new path, or like we'll
No,
try to
you will find
maximize
out the path in the augmented graph.
yeah.
You always find out the path in the augmented graph, not in the old graph or something.
Okay.
Okay. Okay. So where are we now? So okay. So one thing is that this algorithm, so I will call this Ford Fulkerson algorithm. Now see, every time this path finds out a minimum, right, and updates it. So if to start with all the edge weights were integers, then what happens? Then every time if it updates it, it updates by 1 unit, right? Increases the flow by at least 1 unit. So this is assuming capacities are positive. Capacities are integer. But how many times will it increase? And why will it always keep on increasing? It cannot always keep on increasing, right? Okay. Can you give an upper bound on the number of times this algorithm can have to repeat this whole process?
Some of the edge weights starting from
Okay, good. So some of the edge weights. So this algorithm, the Ford Fulkerson, stops after summation of the C of E number of steps. Okay, very good. Why does this Ford Fulkerson gives you the maximum? Why doesn't it stop much beforehand? Now, this is something that I have not talked about, and I want you guys to go and think about it. Okay, so there is a concept of min cut. Okay, min cut is a set of edges, that kind of a set of capacity. So if you can, if I want to break it up into two, if this break the whole graph into two parts, S and T, such that there is partition them, and you look at the set of edges that goes from S to T, some vertex of T. Okay, some vertex in the S component to some vertex in the T component. Okay, then the sum of the edges here is called the cut, size of the cut. Okay,
Do we have to make components such a way that only edges, or can there be paths between these two components?
no, there has to be edges. So you just look at the vertex set into two parts, S union T, that the small s is in capital S, small t is in capital T, and look at the size of the cut ST is the sum of the capacity of the edges UV, where U is in the set S, V is in the set T. Okay, the number of edges that goes from here to here. Okay, now you can define a min cut is the minimum over all S and T, such S and T cut, this summation of these things. Okay. Minimum cut that can happen. Okay, this is a component, that is a property of a graph, a network. So one thing that you can prove, okay, so I will write down two theorems or two observations rather. Okay. First observation is that max flow is always less than min cut. And number two is that Ford-Fulkerson algorithm does not stop as long max flow is equal to min cut. So if the max flow at that time from S to T is strictly less than min cut, then Ford-Fulkerson algorithm will always find a path from S to T and will update it. Okay. So these two theorems I am not proving, or this is kind of an observation. If you understand this whole concept of the Ford-Fulkerson algorithm that was done, then you can understand.
So at every stage, max flow will be max flow of the augmented graph, right?
Max flow is not max flow of the integer. Max flow is the total max flow.
Okay.
I mean, you're finding a path and then pushing some value out of it, right? Putting some path, if you're updating the I mean, you can write, say the max flow of the augmented graph. Okay, fine. I mean, the flow of the augmented graph at that time.
Then minimum cut also should be from the augmented graph only, right?
As long as not max flow, as long as I should write here, as long as flow, okay, is less than the min cut.
Okay.
Okay. So if flow is less than or equal to min cut, then you will be able to find a path.
Fine.
Okay. So what means is that this algorithm that I just described, I have not given you the full proof of it again, okay, is an algorithm that will not only find the max flow, but also since it is updates the flow every time by a unit cost or a integer amount, it will output a max flow which is integer. Okay, so I mean these are observations, and maybe I can write this proof. So okay, so Ford Fulkerson run, okay, outputs and integer flow. Okay, max and integer max integer max. Okay, that is good. So here is an algorithm that outputs an integer max flow. Now, what is the running time of that algorithm? Running time, as somebody pointed out, this is order of summation of C of E, right? In fact, if you want, you can write a slightly better one also. Okay. Now, let me ask you, do you think this algorithm is a polynomial time algorithm?
Depend on the I mean number of bits.
See, again, this is something similar to what was done earlier in one of them. The C's are integers, right? So number of times. So if C is, say, if this quantity is say 1 million, or 100 lakhs, then this algorithm will take 100 lakh steps. But the number of bits to represent all the C's is just 1, 2, 3, 4, 5, 6, 7. So in 7 bits or 7n bits maybe or something like that, I can represent the whole thing. But the number of steps is 1 million. The reason is that, of course, there's a bit representation issue. So this algorithm is not polynomial in the input size. Now there are certain tricks that you can do. So there was this place that I kind of skipped over, is that the first thing that was done is that we were always saying that greedily find a path from S to P. Actually, it turns out that if you do a little bit more than greedily, and if you choose a path optimizing something, so but if a path is chosen with some property, then one can prove the algorithm is polytime. Now, this I am not going to do it in this class, and I think this is already way too much more than what many of you can handle. Okay, so but I am so okay. So what all things have we done now? Okay, so let me just quickly recap a few things that was there we have done so far, and this is something important. Okay, so we had this concept of LP, and we had this paper of ILP, right? And we told that this many problems can be reduced to LP and ILP. Then we had this question of matching. This matching could be reduced to ILP. And we have this concept of flows. This could be reduced to LP. But the reason this ILP came up in the picture is actually that if I move it a little bit here, so matching could be reduced to something called an integer flow, which could also be reduced to ILP. Okay, good. So there, if I have given you just flows, you can solve it in LP. If I give you a matching, you can write it as an integer flow problem, and an integer flow problem you can write it as an ILP. But now I'm using these two terms here, kind of vaguely. I will talk about it later. So this LP is in polynomial time. It's P. P stands for polytime. Polytime or algorithms that can be solved using in polynomial. So maybe that you write it here. I will give you the definition formally next class. So this is algorithms. These are problems for which polytime algorithm exists. This one, okay, let me say that, I mean, kind of, this is not in. I will talk about it again better, but you can think of it that it is not in. So if I try to solve matching or integer flows as an ILP problem and then solve it, then I don't have a polytime algorithm. But it so happens that this integer flows and matching, they are actually in P. It is true that while ILP doesn't have an polytime algorithm, integer flows and matching has a problem, has a polytime algorithm. And these things follow from Ford Fulkerson and some things, plus some stuffs. Okay, I have not talked about everything, but it follows from that. So as a algorithm designer, one thing that you have to kind of remember is that if you can design a problem in LP, then you can make it into polytime. Great. If you can design an algorithm as a matching problem or as an integer flow problem, then also you can do it in polytime. But if you cannot do that, then you can try to write it as an ILP problem, in which case there is no guarantee that you have polytime algorithm, but you have reduced to a more generic problem. So this kind of gives you the idea that choosing what problem to reduce a particular problem to, that is a very crucial part of algorithms.
Sir,
yeah.
Given an ILP, when can we identify that can be made into an integer flow problem? The reverse.
No, an ILP cannot necessarily be made into an integer flow problem. Okay.
What about the coefficients being just ones or something like that?
No, characterizing ILPs which can be made into integer flow program, that is not very easy. Okay.
Okay.
So one thing that you should remember this one, that if you are going anywhere and you are trying to, so your job is not to design a new algorithm, okay, but your job is to solve a problem. Okay, this is something that I'm trying to come up again and again in this last part of this course, which many of you possibly will be taking up this kind of stuff, that you design you don't design an algorithm, but you solve a problem. Okay, your main creative idea or your contribution would be how to reduce it or model it in a particular structure. Okay, if you can model it as an ILP problem, then you have access to ILP solver that can solve it, but they are not necessarily polynomial time. If you can model it as an LP problem, then you are great. Then you have polytime algorithm and done very fast solver that are there. If you can reduce it to an integer flow problem, okay, then it's also is fine. Then you cannot use this one, but then there are algorithms which are kind of standard tools to solve integer flow problems, and that can be done. So your job is to identify problems to which it can be reduced. So at this thing, I should say that LP, ILP, and the integer flow and matching. So matching is a special case of integer flow, are the most important things that we have looked so far in terms of algorithm usability. Okay, these are the 4 problems that are this kind of the cornerstone till now. In the next class, we will be talking about another of those cornerstone problems. Okay, and so what we are now is that, therefore, I can say that if I have to design these problems of P, what all problems are there? There is this LP, there is matching, and there is integer flow. Of course, you can say flow is basically LP, and flow is also a special case of integer flow, so it's fine. And not in P. Now again, this not, I am kind of not saying it exactly not. I will explain you more about it. This is one problem that you have looked into, is the ILP problem. A very, very, very powerful tool that exists. So for all of these problems, there are nice polytime solvers. For this problem, there doesn't exist polytime solvers, but there are ILP solvers which sometimes can give you very quick answer. Sometimes it will not, and in that case, as we discussed in another previous one, it might be good to kind of solve it using an LP relaxation and then try to use that one, and all of those kind of theorems come into picture. Okay. So from the point of view of people who just want to use algorithms for their own future work, job, research, whatever, not in terms of working in the field of algorithms, for them, this is the very important thing to know. Okay, what you need to know is what all things can be done, what are the cornerstone algorithms that are there, or cornerstone problems that are there. I mean, people, for example, have written outstandingly good algorithms for this. Outstanding good. I mean, similarly, people have also written very good algorithms for this ILPL also. Not polynomial time, but something pretty good. Okay. So good. So any questions? Whatever was done today. Hello. Hello.
No question, sir.
No question. Oh, wonderful. So I have a question for at least one of you. Surajit, are you there?
Yes, sir.
So did you talk to your friends?
Yes, sir.
Which all friends did you talk to?
Soham, like no, in CRS batch, whoever couldn't appear the midsem one.
But I told
Soham,
you that this is not good enough.
Sai,
This is not good enough, right? Yeah. So Soham, Sai, and
Orko.
Soham, Sai, and Orko you spoke to.
Yes.
Okay. What about the JRS?
Sir, I didn't talk to them.
Yeah, so I don't know. I mean, like this is something. So this is a which exam do you have on Sunday? Computing system security. What is that?
Computer system security, we have exam. On,
What exam?
mid-sem exam.
It was also a makeup exam.
No, it's a Viva on that is going to happen on 4th July.
On Viva.
Yes.
From when to when?
So it starts from 11.
It starts from 11 and will continue for.
So continue, I don't know, sir.
All of your things will happen in the same day.
Yes.
Who is
Hello.
the teacher here?
Sobhashachi Karati, sir.
Who is the teacher? Who is the instructor?
Sobhashachi Karati,
Sobhashachi Karati.
sir.
Okay, so I don't know. See, you guys have to talk to your friends.
Okay, so
Lakshmikant,
actually I thought
you thought?
that you asked me to consult only CRS group. I didn't understand.
I asked you to talk to your friends. Right?
Yes, sir.
Hello, sir.
Yeah. Hello.
Can you go back to the tower problem and scheduling problem?
Tower problem and scheduling problem. Okay.
Telephone tower problem. Telephone tower problem.
Yeah.
Hello, sir.
Yeah. Hello.
Sir, the mid-sem 2 syllabus will be same as mid-sem 1.
Everything has been written in the email. Okay. So for now, I mean, please talk to everybody in that group.
Okay.
If required, send a mail to everybody in that group.
Okay.
Okay. And
Okay.
quickly get an answer from when this meeting can be held.
Okay, sir.
This is something that if you cannot come up with an answer with your friends, so then it will be held in whenever the IF is.
So okay, I'll talk to them.
Lakshmikantan, are you there?
Yes, yes.
Yeah, can you talk to your JRF friends about this?
Okay, sir.
Yeah, so there are some issues. So maybe you can send a mail to your friends who are in the email list and try to kind of schedule a time which is good for everybody for the taking mid-second. Okay.
Okay, sir.
And yeah, who was asking about the telephone tower problem?
It's me, sir. Sure.
Sorry. Yeah.
It's me. Hello.
Yeah.
So in the telephone problem, do we have to consider it as a directed graph or undirected graph? Because
Okay. I have not told you anything about whether it's considered as a directed graph or non-directed graph. There's no graph here. Okay. You
no,
can
there is no
consider
graph,
it.
but we have to formalize and again
Yes.
try to get
First
back
of all,
to,
it is okay. First of all, the short answer is that you don't. It is a undirected graph. And secondly, did you come to the tutorial?
yes, sir, but he did not cover it properly because minimizing the vertex cover over
Yeah.
entire vertex set is not necessary there, right? Because we have to consider only the vertices where telephone towers are needed, not necessarily the locations. That is
Yeah.
where
So,
the problem arises.
okay. So think about it. Think about it, and you will see what happens.
Okay.
Okay. Any other questions? Okay. So if not, let me stop the class today. And where is it? Okay. So see you on Thursday.